Okay, this is our the first video on u-substitution. I'm going to talk a little bit about the chain rule, and then u-substitution. I'll do a simple example. So here we go. We've been differentiating for a long time, and we finally, when we learned the techniques of differentiation, we got to functions like this one. This is a composite function, and the old rules that we had for differentiating this didn't work anymore. We had to learn a new rule. The new rule we learned was called the chain rule. Oops. Not the chair rule, the chain rule. And the chain rule is used for differentiating composite functions like this one. And what we did was, remember, we look at this and we see it has an inside part, 3x minus 4, an inside function, and an outside function, which is to the fourth power. And the way we differentiated this was in two parts. We first differentiated the outside function, that is this anything to the fourth power, the derivative of anything to the fourth power, you bring down the power and subtract 1. What goes inside here is the inside function, and we didn't touch that. We left that alone. Then we multiplied that times the derivative of the inside, which is, in this case, 3, and we can multiply 4 and 3 together and get 12 times 3x minus 4 to the third power. Now, that is the chain rule for differentiation. What we're going to find is we're going to learn how to start integrating functions that look like this. These functions that we are going to integrate are functions that are the result of having used the chain rule to differentiate. In other words, when we find the antiderivative of this, we're going to use a technique called u-substitution. So in a sense, we could say that where the chain rule is used for differentiating a function, u-substitution is used for undifferentiating or finding the antiderivative of those functions. Let's get to an example. Here we have a function to find the integral of x times x squared minus 1 to the fifth power dx. And the techniques that we have at our disposal so far are powerless to find this antiderivative. What I want to notice here is that the function really looks a lot like something, if we cover up the integral sign here and the dx, this x times x squared minus 1 to the fifth power looks like it was the result of having differentiated some composite function. Okay, let me go back one page here. Notice that what we have, notice how similar it looks to this. We have this inside function, something raised to the power, and something outside. And that's what we have here. We have an inside function, x squared minus 1, and this outside function. Now remember, when we do the chain rule, part of the original, oops, wrong way. When we do the chain rule, part of the original function survives all the way to the end. In other words, this 3x minus 4 slides right through the derivative all the way to the end, and there it is, untouched. You remember this, that part of doing the chain rule, the inside function, survives untouched all the way to the end. Wrong way again. And so the same thing is true here. We're going to look at this as the result of differentiating using the chain rule, and we're working backwards to find the original function. And this x squared minus 1 part is the part of the original function that made it all the way through the chain rule process to the end untouched. And what we're going to do is we're going to call this part u. Okay, so what I want you to do on your papers whenever we do one of these is write this on the side of your paper. We're going to let u equal x squared minus 1. Now the name of this technique kind of suggests what it is we're supposed to do. The whole technique is called u-substitution. It gives us a hint as to what we're going to be doing. First thing is, we're going to take, because this integral is impossible to integrate as it is, we're going to replace it with something that's equivalent, and we're going to take out all the x's and replace them with u's. So what I was saying was we're going to take this integral, which is impossible to integrate, and we're going to replace it with something that is possible to integrate. Okay, so the first substitution is I take out x squared minus 1, and I'm going to call that u. Okay, and now this u I have raised to the 5th power. Now when I do that, I still have this x here and this dx. And you see, I'm not done making these substitutions. I have to find something to replace the x and the dx with. Okay, so I go back to this part right here. Let u equal x squared minus 1. Well, now what we're going to do is differentiate both sides of this equation. Okay, so if I differentiate both sides with respect to x, the derivative of u with respect to x is du dx. And the derivative of x squared minus 1 is 2x. Okay? Now, keep in mind my goal here is to find something to replace the x and the dx with. And you can see, here I have an x and here I have a dx. Well, let's multiply both sides of this equation by the dx. Okay? And the dx is canceled there. And on the left side of this, I'm left with du, and that equals 2x dx. Okay. To reiterate, I've taken out x squared minus 1 and replaced it with u. I decided that this was going to be u because it looks to me like the original part of the original function that survived through to the end of differentiation by using the chain rule. I call that u. I take out the x squared minus 1, replace it with u. Now I need replacements in terms of u for x and dx. And oops, didn't mean to do that. I'm almost there. I have 2x dx, and so what I want to do now is divide both sides of this equation by 2. Now the 2's cancel here, and on the left side I'm left with 1/2 du, and on the right side, x times dx. Now this makes me happy because I'm looking for a replacement, an exact replacement for x dx in my integral, and here it is. X dx is exactly equal to 1/2 du. So this I'm going to stick into my integral, and I'm going to take out x dx, and my integral has become the integral of u to the 5th times 1/2 du. Now all the x's are gone, and all that remains is u. Before I integrate, let me just take this this constant. We know that can come out. We'll put that over here, and that cancels. And my goal was, at the beginning, to take an integral that I could not integrate, could not find the antiderivative of, and replace it with an integral that I can find the antiderivative of. Here I have u to the 5th du. Okay? So this is exactly equivalent to what we started with, but I can integrate this. This is a fairly straightforward. You should be able to do this now. If I take the antiderivative of u to the 5th, add 1 to the power, u to the 6th, and divide by 6, plus a constant. And there is my general solution. Now, it doesn't look much like the solution, and that's because I have to do one more thing here. I started this problem with an integral in terms of x. What I've got now is an integral which is in terms of u, and so what I need to do is what we call back substitute, which means that I just need to take out the u and replace it with the equivalent expression that I got in the first part in x. So I'll take out the u. If I do that, here's what I've got. Okay. Here's where the u went. I take out the u and I replace it with x squared minus 1, because you recall in the beginning of the problem we let u equal x squared minus 1. And here's my answer. I can clean this up a little bit. I'll have x squared minus 1 to the 6th power over 12 plus constant. And there it is.